Hi, and welcome to this video on integration from the Year 2 content of the A-Level Maths course, and this is the first of a series of videos, a subset if you will, on a technique called integration by parts. So, here we go. So that's essentially what we're going to get through over the course of about 4 videos. What we're going to do initially, or what it's all to do with essentially, is this first descriptor, which is how we go about integrating a product. So let's have a look at what we're going to have to do with that. Right, if we start off by thinking about how we integrate, we looked at reversing chain rule, which we were able to do by inspection in a lot of cases. But if we're going to try and reverse product rule, it's just not possible to do it in the same way. So what we're going to have to do is a little bit of rearranging of our product rule, and then some careful choice of what we're going to pick as each part within our product rule gets us around that. So let's have a little look at product rule. There it is. So I'm differentiating the product, and there's our standard leave one or leave u alone, differentiate v, plus leave v alone, differentiate u. What we're going to do is just do a little bit of rearranging, not a whole lot. So what I've done there is just taken this kind of dv du dx term over to the other side. So we've got this term now, the u dv dx, as our subject. And what we're going to do now is take this expression here and just integrate that thing. So we're going to integrate each part. So there we go. So we've got the integral of u dv dx times by dx equals the integral of the differential of uv minus the integral of v du dx, and that's an absolute mouthful, and doesn't look like we've really achieved much. But what I'm going to do is focus on this particular term here. Okay, so let's just think about what happens. If I start off with my product, uv, and I differentiate it, I get d dx of uv, the differential of uv. And then if I integrate that again, I get back to where I started. So this expression here, the integral of d dx uv dx, is simply this thing, uv. So that's going to make life a little bit easier. So let's just do that. And there you go. That is integration by parts. And it might be you're looking at that saying, well, you know what, we don't seem to have done a whole lot because, you know, we've got an integral of a product in here. That's going to be a mess. This one's going to look a little bit messy. It doesn't seem like we've really achieved a whole lot. But trust me, we can make this work just by some careful choice of what we're using in this section here. And I'm now going to do a couple of examples just to illustrate that. So here we go. So what we've got here is a product. We've got a linear function multiplied by an exponential function. So what we're going to do is, let's start off with that one. Now we need to use 4 constituent parts within this. If you have a look at what we've got up here, we've got 4 bits. We've got u, it's appearing there and there. We've got du dx, that's appearing there. We've got v, which is appearing here and here. And we've got a dv dx, which is here. So we've got those 4 bits. And so what we need to do is come up with expressions for those 4 bits. So what we're going to start off by doing is by saying, okay, let's choose that bit. Let's let u equal 3x. Seems like a fairly obvious choice. And therefore that gives us straight away du dx is simply 3. Now if we have a look at what we've got up here, the next bit inside our integral is this dv dx. And that's what I'm going to choose for that bit there. So let's let dv dx equal e to the 2x. And I tend to set these out all the same. In my head, I'm starting off by going down to differentiate and then back up to integrate. So I always set them out this way around. That's just me, but it gives me structure to work with them. So now, if I want to work out what v is, I've got to integrate this thing here. So if I integrate e to the 2x, I get half e to the 2x. And so I've now got my 4 bits. So what I'm going to do now is take those 4 bits and put them into my integration by parts formula. Oh, and by the way, you do get given, don't worry, you don't have to remember it, you do get given that in the formula booklet. So let's put all this together now, and let's see if we can do our integration. Now, these 2 bits here we already chose. So that bit there, the 3x, that's my u. The e to the 2x, that's the dv dx. So that's our subject of our formula, if you will, up there. So that's those bits. So we need u times v, which is 3x. There's our u. There's our v, half e to the 2x. Minus, now we need the integral of v du dx. V is that bit there. Du dx is that bit there. So let's put those in. There's v, there's du dx. And now what we've got is essentially a kind of second round of integrating to do. It's always going to be this second integral that is the thing you're going to have to keep an eye on. But as it turns out, this thing now is a whole lot more simple. Let's just do a bit of tidying up. And what I've done there is just tidied up this term, and I've taken the 3/2, 3 times a half. I've taken that outside the integral because in my head it's just a whole lot easier to deal with constants when they're outside the integral. And you can see now what we've got here, we're left with just the integral of e to the 2x, which is fairly simple and straightforward. So off we go again. Let's go for our second round. That first term stays exactly the same. We haven't done anything with that. And then we've got 3/2 times by the integral of e to the 2x. Integrate e to the 2x is half e to the 2x, so now we've got minus 3/4 e to the 2x, and stick on the plus c as our constant integration, and there we go, we are done. Now, that might seem horribly complicated, but it's all, for me, it's all about the structure, it's all about getting this set up right first, and then just plugging the bits and pieces into your formula, and then tidying it all up, and away you go. Right, let's have a look at another one. Now this one, there's going to be an extra level of complication, so it might be a good idea for you guys, if you want to just kind of pause the video and just make sure you've got the basics sorted and have a practice on these kind first of all, before we get into something like this, because like I said, there's an extra issue in here, which is why I've included it. But if you're happy, let's crack on. So off we go. Now notice again, this one we're doing it between limits, and we've got x squared sine 4x to integrate. So same as before, so let's let u equal x squared. Gives us du dx equals 2x. That means dv dx of it here is going to be sine 4x. Integral of sine is minus cos. So we've got v is minus 1/4 cos 4x. So those are our 4 bits. Let's whack it all together. So we've got, again, u dv dx. So the first bit I need is my uv, which is that one. So uv minus 1/4 cos x times by x squared. That's that bit there. Minus the integral of v du dx. v du dx. So let's put those together there. Now, first thing is just a little bit of tidying up, and a couple of things to notice. We've got a minus and minus, which makes that from there a plus. And also what I've done, I've taken the 2 and the quarter, that's a half, and I've brought that out the front just to get my constants out of the way. And what that's left us with is an integral here, which is x cos 4x. Now that again is a product. So what we're going to have to do is apply exact the same thing. We're going to have to apply this rule again, but just to this part of our expression here. So essentially, we've got to do kind of almost like we're on to like a third round of integrating now, so we've got to do integration by parts on this bit within our result. So let's do that. That's what we had from last time. Notice at the moment I'm not worrying too much about my limits. I'm going to plug those in later on. Let's just have a look at what we get from integrating this bit here. So I'm going to tootle off to the right hand side and do a quick bit of integrating on x cos 4x. So off we go again. Let u equal x, du dx equals 1, dv dx is going to be the cos 4x, integrate cos 4x, I'm going to get the quarter sine x, put it all together, so we've got u times v, so we've got a 1/4 sine 4x times by x, that's that bit there, minus v du dx, that's that, and then I've got the integrating here to do, which is now doable. So essentially that's just a constant there, and integrate sine of 4x. And what we end up with is cos 4x, but of course integrate sine, you get minus cos, so that's caused the change of sign there. And we've got the quarter coming from here, that gives us the 1/16. So all of that now, this expression that is in green down here, I'm going to substitute back in up here, because that is the integral of x cos 4x. So we've got my initial part there, which I haven't done anything with. There's the half times by this integral here. So that's the bit I've just integrated. And then multiply out the bracket. So half times 1/4 is 1/8. Half times 1/16, 32. And I've done all my integrating now. So I've got square brackets, and I've put the limits back in. Right. Having done all of that, so what we've got to do now is put in my limits. So let's plot pi over 4 and 0. So again, it's you've got to show clearly that you're in substituting your limits and the intention to subtract. So showing clearly also that I'm sticking in zeros into here, even though these things in the main are going to become zeros. But let's just have a look at what we've got going on in here. So we've got cos pi is minus 1. sine of pi is 0, and we've got a -1 there. So let's chuck those values in. You'll notice that first bracket here we've got the quarter pi squared, that's our pi squared over 16. But notice because we've got cos pi is -1, that's dealt with a minus sign there. We've got a 0 there, -1 over 32. And then let's have a look at what's going on with the second bracket. That one there is 1, cos of 0 is 1, sine of 0 is 0. So let's put all that in, but having said that, we've got a 0 there and a 0 there, so really it's only that term that we're going to be left with. So there we go. So now just put that together, and there we go. We've got pi squared over 64. We've got -1 over 32 there, minus another 1 over 32 there. So that's -2 over 32. That's -1 over 16. And there we go. Jobs are good 'un. Now that might look like a shocker, but it was just to do with that kind of second round of integrating. And the reason it's happened is because if we go back up to this x squared here, we need that to effectively disappear in this second part of the integral. So we need to do it twice, because when we differentiate x squared we get 2x, so we're still going to end up with a product. But then when we differentiate 2x, it just becomes a constant, and that allows the whole thing to disappear. So when you're choosing your bits at the start, you need to be choosing a value of u, or u such that at some point you can differentiate it and continue to differentiate until it becomes a constant, and then that allows you to proceed. Cool.